Okay, Siba, would you be so kind as to read the first question for us?
Object A of mass 2.5 kilogram with a speed of 30 meters per second collides with a stationary object B of mass 4.5 kilograms. After the collision, object A has a speed of 5 meters per second in the opposite direction to its original path. A1, determine the magnitude of the initial momentum of object A.
Okay, so at the beginning, the momentum of A is just going to be mass of A times velocity of A. 75, is it? Kilogram meters per second. And then let me guess, is part 2, what's the speed of B? Yeah, so yeah, it's going to be conservation momentum. So that's m1 u1 plus m2 u2.
U1 is V. Is 5 minus 5.
No, that's I think that's v1, isn't it? Isn't it the minus 5?
Oh,
Yeah. So that's 75 plus what's 2.5 times 5? 12.5, isn't it? And then if you divide that by 4.5, you can get your x. So what's that? 75, 87.5 over 4.5. What's that? What's that again, Siva?
I think 75 minus.
Did you put minus 5 or 5?
This is the opposite, right?
And bring it to the other side, it comes plus? It is plus?
Yeah.
Okay, so what's the x here?
It's
What is it?
19.4.
Okay, did anyone else get this? 19.4? Yeah? How many marks for A1?
A1 1, A2 2.
Ah, only 3 marks. Okay. Alright, Kim, can you read us A2, please?
There's B.
Oh, there's a B part for this? Ah, go on, Siba.
State whether this collision is elastic or inelastic.
It's probably inelastic because the energy before the collision, which is a half a half v squared. I have a feeling that would be bigger than a half 2.5 times minus 5 squared plus a half times 4.5 times 19.4 squared. Oh no, maybe I'm wrong actually. It is bigger, so that makes it inelastic. Is that the end of A1 now? Okay, Kim, A2 please.
Find the moment of a force about point.
Oh, define.
Yeah.
So define, what did you say, define the moment of a force?
Yeah.
Yeah, so the moment of the force is the force, let's be a bit more formal. The product of force by perpendicular distance to turning point or pivot. The product of force by perpendicular distance to the pivot. So in other words, it's F times D. So you have your distance and you have your force there. Okay, what else is there?
A crane is used during construction to lift boats as shown in the diagram.
So it's like something like this, is it? Yeah. And what do we know? Do we know this length? On the top? This length?
10 meters.
That's 10 meters? Yeah, and do we know this length? Or we don't need to know it? Or
No length for that one, just the mass.
is the mass here? Yeah, what's the mass?
Different in two pistons.
There's 2 different masses.
No, there's just one. It's 10 kilonewtons.
10 kilonewtons. Right, so what's the question? What are they asking for? Go ahead, Kim.
If the load being lifted is 10 kilonewtons.
Yeah.
And distance d is 10 meters.
Yeah.
Determine the moments of the weight of the load about point x.
Determine the what? The moment. Okay, that's 100 kilonewton meters. Right? That's it? How many marks was that? One. Yeah, okay. Is there more?
Yes.
Okay.
If 10 kilonewtons is the maximum load that can be safely lifted, when d is 30 meters, determine the maximum safe value of d when the crane is lifting a load of 20 kilonewtons.
Say that again. When it's lifting a load of 28 kilonewtons, is it? Is that what you said? Yeah. And what did you say?
30.
30. And what do they want?
Safety value?
Save value of D when the crane is lifting 20 kilograms.
Right. Okay. So I have a feeling that if we did 30 times 28, what do we get there? We don't get 100, do we? What do we get?
20.
Oh, it's 20.
20.
Okay. We get
I think it's 10 kilonewton is the maximum load that can be safely lifted when D is 30.
Yes.
Oh, I have my picture wrong. So what they're saying is when D is 30, yes, you can lift how much? 10 kilonewtons, okay. So what's the turning force here? That's 300 kilonewtons, yes? Kilonewton meters. That represents the maximum for safety. This is the limit. And their question must be, if you're lifting 20, yeah? Yeah, if you're lifting 20 kilonewtons, what's the distance here? Yeah? So the idea is that turning force can't exceed 300 kilonewton meters. So it's D times 20,000 must equal 300,000. So D is 20 over 300, which is 2 over 30, which is 1 over 15, which is what? 0.
3 over 2.
Thanks. I have that upside down, don't I? Thanks. Let me just lazily fix that. So 15 meters. 15 meters. Thanks, Andek. Is that A2 finished? Yep. Okay. Chow, give us A3.
A mass of 3 kilogram on the spring X. What's this?
Extended.
Executus.
What word is that? Execute. Okay.
Executes a simple harmonic motion of amplitude 2.5 cm at a frequency of 1.5 hertz.
Good. And what's the question?
Sorry.
Yeah.
Determine the maximum velocity of the oscillating mass.
Okay. So do you remember the formula for this? The maximum V? Very good, very good. A omega. Do we know omega? We can know it. Omega is 2 pi over t. Do we know the t? We can know it. We don't know it. It's 1 over f. So it's 2 pi AF. So that would be 2 pi 0.025 times 1.5. Right, do you have that, Siba? It looks like you do.
0.236.
Okie dokie. Next part, Chow. Part 2.
Sketch a graph of kinetic energy against the time for one full cycle of this.
Okay. So at the very beginning, do you pull the spring down, is it? And let go? I imagine probably. Does it say that in the question? What do we think?
Including values of the maximum kinetic energy and the time point.
Ground, okay, we can do that. But I'm trying to picture the spring. In the story, does it say somebody pulls it down and lets go? Or, like, how did they set the story up? What did they say, Siva, at the beginning?
Sketch a graph header.
No, at the very beginning.
A mass of 3 kilograms on a spring executes simple harmonic motion of
So they don't tell me how it came into being. So what I'm going to do is, I'm going to imagine, I don't know, like, I'm going to imagine somebody came along and pulled it down and held it, and then they let go, and it started going up and down, okay? So, at the beginning, you don't have much kinetic energy. So, like, if you picture it, you let go, kinetic energy? No. Then, faster, 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 slower, slower, stop. So that's one half. And then it's up here, and then what happens to the kinetic energy? Faster, 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 faster. And then slower, 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 stops again. So it should look like this. No, it's not getting faster, sorry. It should look like this. And this here is the time. The time is 1 over f, which is 0.667 seconds.
Yeah.
And this is the maximum kinetic energy which they want you to calculate. So that's, what's the mass of this, did we say? 3. So can you just type in 1.5, that's a half 3, times 0.236 squared. 0.0835 joules. Okay. Is there, yeah?
If I write time on y-axis,
No, 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 no. 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 That is very, very Hafren. Isn't that the word? Very forbidden, Matt. Very forbidden. You go straight to physics hell for doing that. Alright. Is there more to it?
No.
No? Okay, so what number are we on now?
A4.
A4. Okay, go ahead, Andek there.
State 2 assumptions made in the kinetic theory of gases.
Okay, does anyone remember 2 of the assumptions? This is the lesson where you had, we were looking at the gas like this.
Moves in another direction.
Yeah, yeah. No, gravity was one of them. I think the one, I mean, they said state 2 and you have more than a choice of 2. I think the one that this person likes is the fact that they are elastic, so the collisions are perfect collisions. And the other thing you said, Siba, whoops, you said no gravity. So we'll just make this a little bit more general. We'll just say no force between the particles. Just the same idea as what you said. So no, yeah.
So it has no force between particles because there's no gravity.
Yes, yes. I'm just trying to keep it general. But there's other things too. The motion is random. What else did we say? No potential energy, wasn't that one? Low density, that's the other one which is important. There's 3, low density. Okay, what's next, Andek? Or was that it for A4?
No, there's no.
Another part of A4?
Yeah.
Okay, what's next?
In terms of kinetic theory, explain why in a phase volume container of ideal gas, the pressure increases as temperature increases.
Okay, so What was it? Temperature equals 3 over 2 K kinetic energy, wasn't that it? Average kinetic energy. So that means that temperature is proportional to kinetic energy. Yes? So increase KE means increase T. Right, that's it? That's it, I think. Isn't that what they ask you to
Yeah.
yeah.
They want us to explain why it's not kinetic theory.
This formula comes from the kinetic theory. If you want, the other way you could do this is just write it out, explain it. So you could say like temperature is a function of the
Can I mention that temperature provides more energy to particles than
you could say which way around was it, that they increase the temperature and the kinetic energy increases, or the other way around?
temperature and energy.
Okay, so you could write it out as a sentence rather than as a formula. So the increase in temperature provides more energy to the particles. They increase their kinetic energy and so they move faster. Is it that you have to say they move faster or they have more kinetic energy?
Well, the pressure.
Oh, pressure!
The pressure increases.
Oh, well then I'm not finished. Sorry. I thought you said kinetic energy. So I need to start again. Sorry, I misheard you. So let me just be super clear. You need to prove that if you increase the temperature, then the pressure increases. Is that it? Okay. So you have a couple of formulas that might help you prove this. You have the good old PV equals nRT. That's a good one. You also have PV equals, what's the other one? 3 over 2 KE. Isn't that one? Isn't that one of them? I think so. And then, or is it 3 over...
I think it says thermal kinetic theory.
Oh yeah, that's fine. I'm just trying to jog my memory of the 3 formulas we need. Is that one right? PV equals 3 over 2 KE. And there was another one that T equals 3 over 2 KE. Was it? I wish I had my formulas in front of me. Do you have them from this lesson? All the way back from semester 1? Maybe I have them in my book here. Can't remember them. I'm so tired. Let's see. Materials was our second chapter, wasn't it? No, I don't have them. Do I need to know it? No, I suppose I don't need to know them. Screw that. I have enough with this formula, don't I? Yeah, because if I rearrange this, I can get P equals NR over V, T. So, if V is fixed, and of course N as well, but usually it is because you're not letting anything leak out, then that means P is proportional to T.
Sorry, NS?
Number of moles. Okay, so that's it really then. So it just comes from the ideal gas law. I need to remember those other formulas. What are they? PV equals 3 over 2E. I'm pretty sure it's one of them. And then is the other one like T equals 3 over 2KE or something? Or 2 over 3? Can't remember. KE equals 3 over 2 RT. Oh, don't mess with me. Alright, is that the end of that question?
Yeah.
Okay. What number are we on now? Have we got time? No, okay. Well, I'll tell you what, I'll just finish with number, well, is number 5 big or small? How many marks?
5.
Oh, okay, no. We'll just continue with number 5. How many hours have we got tomorrow? Alright, so I'll finish section A tomorrow and then we'll have a look at the lab report. What did we do last week? We did the... No, we did the planning. We did the planning, didn't we? Yeah. Yeah, okay. So, what is it for next week? Oh, it's on my computer. All right. Tomorrow, I mean. Sorry, tomorrow. All right, bring your laptop for tomorrow.